the company to the ads organization. That's where I started. And I've worked on Android. Recently, I concluded with a collaboration with the cloud team to build some machine learning tools for small and medium-sized businesses. Also, since joining Google, I've taught several classes internally on machine learning. And so some of the material that I'm going to present today is based on that curriculum. Say a little bit more about this talk. So first of all, I should warn you at the outset, the talk is exclusively technical. It's not really intended for a general audience. I gave this talk originally to a group of tech workers at a bank who were interested in machine learning but didn't know too much about it, but they wanted to learn about it and they wanted to apply it to their own jobs. So it's a technical talk. It would be helpful to have some background in math, computer science, statistics, something like that. I don't think it's necessary. I think you will be able to get something out of it even if you don't have that background, but we'll see. It doesn't assume any knowledge of machine learning, so you don't have to know anything about machine learning coming into the talk. Towards the end of the talk, I'll say a little bit, I'll just offer some opinions about the field and where I think it's going. So just be warned that some of the content of the talk is a bit subjective. And finally, the material is a little bit out of date. And I think it really speaks to how quickly this field is evolving, that in the time since I first prepared these slides, which was about 2 years ago, the field has advanced so quickly and so rapidly, and there's literally been breakthroughs just in that time, that some of the material I'm going to present to you has already been superseded by even more sophisticated algorithms and techniques. So I'll try to hint at that a little bit, but just be warned, this field moves very, very fast. And so some of the material out of date. Oh, I see we have more participants, even though I didn't admit anyone. So people are somehow making it in, right? Okay, good. Okay, so just to kind of clarify the terms that we're going to be using, you may have heard, you heard of machine learning. You've probably also heard of artificial intelligence. You've heard of data mining. You've heard of data science. And you're probably wondering how these things are related. There's a lot of overlap. Oh, also information retrieval, that's another one. So all of these terms, I would say, are pretty closely related, and there's a lot of overlap between them. And particularly machine learning and artificial intelligence, I would say the distinction between those terms is not really technical, it's almost like political. So way back in the day, back in the 50s and 60s, people talked about artificial intelligence. They talked about building machines that were smart and could think. And there was a lot of hype around artificial intelligence, and it was overhyped, and AI was overpromised. And it didn't really deliver back in the 50s, 60s, 70s. And so there was a stigma, if you can believe it, there was a stigma attached to artificial intelligence research back then. And so researchers realized that they kind of needed to rebrand themselves. If they wanted to work on this, they had to tell funding agencies and the general public that they weren't working on AI, they wanted to work on something else. And so they started talking about machine learning. But really, machine learning is just the next step of artificial intelligence. They're all kind of the same thing. And more recently, the technology has caught up to the hype, and now AI is really taking over. And so the term artificial intelligence has been rehabilitated. And now, I'm sure all of you have heard a lot about it. And so this is a graph of the use of AI and machine learning over time. You can see it was very popular back in the 80s, then it kind of crashed because it overhyped and underdelivered. And then if I were to continue this graph, you would see artificial intelligence pop back up again as it became more popular. I heard something. Is that a question or just someone? Okay. So, so in this talk, I'm going to talk about different machine learning models. I'll start with shallow models, then I'll go on to deep learning, which maybe some of you heard about. I'll talk about a little bit how you can train these models, and then I'll talk just a little bit about what the next steps are for the field. So, a shallow model. What is a shallow model? So I'm gonna just describe a machine learning problem, the most elementary, simple machine learning problem that any of us can think of. So imagine the problem you're faced with is you're given an image of a digit, a handwritten digit, 0 to 9. It's grayscale, just to make things really simple. So it's just a black and white image. And you want an algorithm that predicts whether this digit is the number 3 or not. That's it. Just one simple question. So in any machine learning problem, we've got our input and we've got our output. And our input is a set of features that describe the thing that we're trying to make a prediction about. And the output predicts what the label of this thing is. So in this case, the input is a grayscale image, so it's an array of pixel values. Each pixel value represents the intensity of the pixel in the image. Higher intensity means a lighter color. That's the input. And the output is a label 1 or 0. Conventionally, we use labels like 1 and 0 to indicate whether the input is what we're trying to predict or not. So in this case, the number 1 indicates that this digit is indeed the number 3. And if it's a 0, then that indicates that the digit is not the number 3. So at the bottom of the slide, I've given you 2 examples with their labels. Any questions on any of this? I can't see any of you, so I don't know if there's confusion or anything. Guess not. Okay. Okay. So, so how might we take this input and generate a prediction? So I'm just going to literally tell you, without much preamble, exactly how these models work. So if I've got an array of pixel values, and I want to predict whether this array of pixel values is a 3 or not, the model that I use is represented by an array of weights. And I've got 1 weight per pixel. So if let's say my image is 16 by 16, okay? So that's an array of 256 numbers, that's 256 pixel values. I'm gonna have 256 weights as well, 1 corresponding to each pixel value. And I just multiply for each of these pixel values, I multiply it by its corresponding weight. Okay, now I've got a whole bunch of products, 256 of them. I add those weights up, or I add those products up. And if that sum is more than a threshold, I say, yes, this is a 3. Otherwise, I say it's not a 3. Okay, now this seems like an unmotivated way of doing a prediction. But if you think about it, this is a lot like how a neuron in our brain works, right? So neurons, they've got dendrons and they've got axons. So like, what is a neuron? So it takes input signals from other parts of the brain, and its inputs are called dendrons. And it just takes electrical signals that come into the neuron, and it's got a whole bunch of these. And then if those electrical signals all together are above some excitation level, then the neuron outputs, and then we say the neuron fires and it outputs an electrical signal along its output, just call that its axon. And so our model works, the model I just described works very much like that. You've got your input signals, those are the pixel values for the image. You've got these weights associated with the pixel value, which I'll talk about a little bit more in a minute. I'll say more about what the role of those are. But you got your input values, those are your signals. You multiply that by the weights, those are your input excitation values, and you just add it all up. And if it adds up to a lot, you say it's a 3. And if it doesn't You say it's not a 3. Okay. Okay, no questions? Nothing? Anyone confused? All right. So these weights, right? Like what would a good set of weights be to predict whether a digit is 3 or not? So let's think about it. So I want the sum of those weights times pixel values to be large when the input is 3, and I want that sum to be small when the input is anything other than a 3. So if you just think about it for a second, what you probably want to do is you want to have large weights where 3's, an image of a 3 tends to have large pixel values. And you want to have small weights where images of 3's tend to have small pixel values. In other words, you want to have large weights where the image is bright when it's a 3, and you want to have small weights where when the image is dark, where the image is dark when it's a 3. Why is that? So if you take your pixel value and your weight, and if you have a lot of overlap between those two, then you're going to be multiplying large weights by large pixel values everywhere in the image. And so you're going to have a lot of big numbers. So when you add up all those numbers, you're going to have a big sum, and you're going to probably be above that threshold, and you're going to fire the neuron. On the other hand, if there's not a lot of overlap, if the large weights align with the small pixel values and the small weights align with the large pixel values, then those products are all going to be pretty small. And when you add them up, that sum is going to be small. And so you're not going to get the neuron to fire. Any questions about any of that? And so, therefore, a good set of weights is going to kind of look like a ghost 3, where you're going to have larger weights where 3's tend to be and small weights otherwise. Now, we just talked ourselves through what a good set of weights would be. And like for simple images like handwritten digits, it's pretty easy to kind of imagine what a good set of weights would look like. But for more complicated images, it's not going to be easy to manually specify the weights of the model, especially if the model has a lot of weights, if the image is very large or very complicated. So in general, instead of just kind of thinking about what a good set of weights would be, we learn them. We estimate them from data. So how do we do that? So what we do is we collect a lot of examples of images. So in this case, lots of handwritten digits. And we label them. We say which ones are 3's and which ones aren't. And we collect that data set. We call that our labeled data set. So here I've labeled them XXI, right, for the ith example. And so here X is the pixel array for the input image. And then label is XI is the ith image, and label I is the ith label for that image. And then I just try to find a set of weights so that the prediction on this data set, the error on this data set is as low as possible. So I give it to my algorithm, I give it to my learning algorithm. My algorithm searches through the sets of weights and tries to find a set of weights so that that neuron fires on 3's and does not fire on anything other than a 3. Okay. That's it. That's actually machine learning in a nutshell. So if you wanted to quit this talk right now and take nothing else away from it, you would basically understand how machine learning works. You have models. Models are specified by weights. Those weights yield predictions. We have a way of measuring how accurate the predictions are, and then the algorithm searches through the sets of weights to find the most accurate model. Is there a question or just random noise? I guess just random noise. And this problem, by the way, of recognizing handwritten digits is probably one of the oldest and most successful, or I would say the earliest successful widespread application of machine learning. I think it's back in the 90s when banks started using machine learning models to recognize digits on checks, handwritten digits on checks. And also the post office started using machine learning models to recognize zip codes on envelopes. So this, I think, is like the original success story of machine learning. This is from back in the 90s. So now that's the simplest possible machine learning problem and the simplest possible way to solve it. There's lots of other different kinds of models that aren't shallow models, like the one I just described. There's lots of other kinds of machine learning problems too, like rather than just predicting whether something is in one of two classes, you could try to predict whether it's in one of many classes. Like, given an input image, is it one of 10 possible digits? That's multi-class learning. Then there's semi-supervised learning. So the example I gave you is supervised learning, where you're given a data set and you know which class every item in the data set belongs to. That's supervised learning. In semi-supervised learning, you're given some data that's labeled and some data that's not labeled, and you're asked to do the best you can using both of those data sets. Then there's active learning. Active learning is when you, rather than being just handed just like the static batch of labeled examples, you actively ask, what is the label of this example? What is the label of that example? And your algorithm has to make those decisions in a smart way. Then there's structured learning, or structured prediction, where the label that you're predicting is some complicated object. Like, like if you're given a sentence and I want to parse the sentence, like grammatically, like I want to know what is the relationship between all the words? What is the subject? What is the verb? What is the object of the verb, etc. So that's a label, that's a prediction, but it's a complex structured prediction. It's not just a simple, yes, it's a 3, no, it's not a 3. And so there's lots of other topics in machine learning that we could cover. And what I just gave you a rundown of is kind of like the greatest hits of machine learning up to, let's say, 2009, 2010. Okay, that's kind of like where all the action was in machine learning up until that point. And then around 2010 or so, there was a new approach to machine learning that really took off, and it's completely revolutionized the field, and that's called deep learning. And so for the rest of the talk, I'm going to talk about deep models of deep learning. Okay. So what's deep learning? Well, so remember I described that simple shallow model that was inspired by the operation of a single neuron in our brain? A deep model just consists of many, many shallow models all hooked up together in many layers. And the fact that there's many layers is why we call it a deep model. So if you look at this image, look at maybe the blue circles and the pink circles, not the yellow ones. The yellow ones are the input. They represent, like, say, for example, the input pixel values of an image. And then the blue circles next to it, each of those is a neuron, just like the neuron that I described earlier in some detail. And each of those neurons takes as input the pixels of the image. But rather than having just one of them, we have a whole bunch of them. And rather than each of them outputting a prediction, they output the input to the next layer of the model. And so that next layer also consists of neurons. And that outputs, in turn, another set of inputs to the next layer, and so on, until the end, when you get a bunch of outputs, in this case, 3 outputs. So this is, again, and this is historically, this is even more directly inspired by the way our brain works. So our brain is not just a single neuron. It's a bunch of neurons that are all hooked up to each other, and the signals that are fed into one neuron possibly excite the neuron, it outputs a signal, and then that signal is input to another neuron, and so on, until some part of your brain is excited, and that, like, let's say you look at a cat, right? So, you're looking at a cat. There's some signals in your eye that propagate to some layer of neurons, and that gets propagated and propagated and propagated until there's some part of your brain that gets excited and says, oh, that's a cat. So as I said, so this idea of hooking up neurons into a large, deep network is not a new idea. I'll say more about that later, but it's definitely not a new idea. But we didn't really get it to work. It took a really long time to get this to work. And it was only around the early 2010s that people really were able to train these models efficiently and effectively, and started making real progress on real problems. And probably the first major breakthrough was back in 2012. It was this deep model called AlexNet. And so every year they have these image recognition competitions in the academic community. And in 2012, they entered a deep model that won the competition by like leaps and bounds. Like they took the error rate, the state-of-the-art error rate in this competition was 25%, and they took it all the way down to 15% in a single year, which was an enormous improvement. That was probably the first time people really woke up to the potential of deep models. And these days, the current state-of-the-art on this data set for image recognition is about 3%. Deep models are now being used in all areas of machine learning, and in just about, well, not just about, but in many, many, many areas they have made just like leaps and bounds in the improvement of the accuracy of the models. So they're also used in speech recognition systems. And so here's a picture. So at the bottom, we've got the input now is no longer pixel values. These are like acoustic signals, like frequency and amplitude of some sound signal. And then it gets input into the first layer of the model, and then that propagates and propagates and propagates. And then, well, at the top there's something more complicated going on. But that's the general idea. Like it's a deep model that takes as input acoustic signals and outputs a prediction of what word you're saying. And so I was talking to someone about this, and they said that once they switched from what they were doing before to deep models, they made as much progress in a single year as they had in the previous 30 years. So, and deep models are used in all kinds of other fields as well. All areas of natural language processing, vision, I don't know, you name it, that's deep models are being used there. At Google, we use deep models to do something as kind of prosaic as predicting whether you're going to click on an ad. So that's the state-of-the-art performance is obtained there by deep models. So why do deep models work so well? Well, there's a lot of theories. One of the interesting things about machine learning these days is that we have technologies that work really well, even though we don't totally understand why they work so well. But anyway, so one of the major theories is that the deep model enables what we call hierarchical prediction. So let's think back to our shallow model, right? That was just a single neuron. So that neuron, it took in, it inputted an image, and then just in that one layer, it had to figure out whether that image was the thing that it was looking for, like a 3 or not a 3. In a deep model, the workload, if you like, is spread across many layers of the image. And what you find is that the initial layers tend to look for primitive characteristics of the image, like where are the edges? Where are the corners? Where are the circles? That's what the first layer of the deep network will do. That's what the neurons in the first layer are trying to predict. They're not trying to figure out, is this a cat? They're just trying to figure out, okay, this patch of the image that I'm looking at, does it have an edge or does it not have an edge? Does it have a square? Does it not have a square? Just really simple things. And that information is then output to the next layer. And the next layer can say, okay, I know where all the edges are. The input signals from the previous layer are telling me where kind of like the primitive features of the image are. Now can I figure out, okay, this looks like a hexagon or something. Now I can take all these edges and say, okay, this looks like a square. And then I can propagate that further, and some more subsequent layers are able to make more sophisticated predictions about what shape is in the image based on the input from the previous layers. And I'll just stress again, this is an emergent property of the network. We don't go in, we don't say, hey, first layer, you should be an edge detector, and second layer, you should be a square detector, and so on. We just give it loads and loads and loads of data, and we ask it to find the weights that minimize the prediction error on that data, and we find that the network tends to have this property. That the first layers look for primitive features, and the subsequent layers look for high-level features. So there's lots of different kinds of deep models. The original deep models, the oldest deep models are called feed-forward neural networks, and those are the neural networks that I've been talking about up to this point, where you input the input for each layer is taken from the output of the previous layer, and you just stack layers on top of each other until you get an output. And image recognition models, which is the running example I've been using so far, tend to be feed-forward neural networks. Another popular architecture is recurrent neural networks. So a recurrent neural network is one where you take the output of one layer and you feed it back in to the previous layer. So in other words, it's a neural network that has loops. So on the left-hand side, I've depicted, this is sort of a shorthand way of depicting what the deep model looks like. And another way that people often depict this is to take that and unroll it, just pictorially, so you can see what's happening. So this is saying, okay, I take one element of my input, I feed it into the network, I get an output, but I also feed it back into the next, feed it back into the network again. And when I feed it back into the network, I take the second element of the input, that's X1, and so on and so on and so on. So in the abstract, that's a little bit confusing, but this kind of recurrent model is often used for sequence-to-sequence prediction, like machine translation. So I'll give an example. Okay, so here's an architecture that was state-of-the-art, I would say, maybe a year and a half, 2 years ago, for doing machine translation. And it uses a recurrent neural network. And this is a simplified description, but this is basically how it works. So I've got my network, and it's got input and output, and also sometimes the output feeds back into the network. Okay. And the way I translate is as follows. First, I input every word into the network, and I just feed the output right back into the network again. So let's say I'm trying to translate the word I think, therefore I am. So I feed the word I think, therefore I am one at a time. Each of these words generates an output, and every time I input a word, I feed the previous output back into the network at the same time. So I've kind of run the network, 5 times? I run the network 5 times. So at the end of those 5 steps, I have an output that, if you like, you can think of it as the meaning of the sentence. Because this network has now ingested the entire sentence, and it's seen all the words in it. And so now I think of this output as being the meaning of the sentence. Then in order to translate it into some other language, like French, I take that meaning, which is just the output of the network, and I feed it into another neural network, and I just do it another 5 steps, and I get and every time I feed it in, you output one word of the target language. And so now this recurrent output that you're feeding back into the sentence, you can think of it as the meaning of the sentence that I've left to translate. So if I have already output je pense, then the network should output an output that represents what I have left to translate, and that's what I feed back into the network. And it says, oh, okay, I have left to translate, therefore I am. And so it knows that it needs to do that. So first of all, let me make a couple of comments about that architecture. First of all, it seems like it couldn't possibly work because it's so kind of simple, right? It just seems kind of, I'll tell you, when I first learned about this architecture, I was like, there's no way that could work. It seems kind of hokey. It seems to boil down the problem of machine translation into something very reductive. Like, how can I represent the meaning of an entire sentence as the output of a single neural network, no matter how deep it is? It's also, well, yeah, I think that's the main comment. It just doesn't seem like it could possibly work. But as I said, as of like a year and a half ago, this architecture was basically state of the art in terms of machine translation. So here's an example. So the top sentence is some text in French. The middle sentence is the output of a deep model that works basically like the model that I just described. And the bottom sentence is the truth. So I'll let you guys just look at that for maybe half a minute, and you can decide for yourselves how good this translation is. I think it's pretty good. I mean, considering how simple the model is, I think it's not bad. Oh, and let me stress again, the way that I describe the model, right? Like, I say, okay, the output of the first part of the network is the meaning of the sentence so far, and in the second part of the network, the output is the meaning of the sentence that's left to translate. Again, these are emergent properties of the network. We don't tell the network this is what the output needs to represent. We just wire up the architecture in a certain way. We give it loads and loads of data, and we ask, find the best set of weights that matches the data. Like, we give it lots of parallel text. We give it lots of English and French parallel text, and we say, just find the best set of that accurately predicts the right translations. And so when we ask the algorithm to do that, we find emergently that it designs the weight so that the network works this way. But we didn't tell it to work this way. Okay. Let me say a few more deep models. Okay, so again, here's another deep model, right? It's a feed-forward neural network. We've seen this before. And so far I've talked about models where, you give it an input and it gives you an output, and it's the output that you care about, right? You're trying to predict something interesting, and you want to design the model and tune the weights so that it predicts that interesting thing. But sometimes actually it's the action in the middle of the network that is more interesting than the actual outputs. And I'll give you an example. So suppose my input is a bunch of sentences that have words that are missing. Okay, so I just collect a whole large corpus of text. I delete a bunch of, I split it up into sentences, I delete words from the sentences, and then I ask the model to predict which words were deleted. And then I tell it, like I give it examples of, okay, here's a sentence, it has a blank in it, and here's the word that I deleted. Tune the weights of your networks so that the prediction that you have for the blank matches the word that I actually deleted. Okay, so now, first of all, this is a weird problem. Like, why would you ever want to solve this problem? If you have your original text, no one ever gives you text with blanks in it. So what's the point of solving this problem? Well, what happens is that, as I said, like, the network tends to, when you ask it to solve a problem, it tends to generate these internal representations that are interesting and can be used for other purposes. Like, for example, in the translation example I gave you a moment ago, like the internal representation represents the meaning of the sentence in a certain way. And so sometimes just looking and using that internal representation can be useful for other applications. So I'll give you an example. So I've got my network, right? And I train it on this text to predict missing words. And what I find is the internal representation of the words has kind of an interesting geometric, gives you kind of an interesting geometric relationship that reveals something about the meaning of the words. So like, okay, so I've got my network and I train it on this problem. The internal representation is a vector of numbers, so I can represent that as a vector in space. And I find that similar words have similar geometric relationships when I look at them as vectors in space. For example, let's look at the top left part of this picture. So if I look at the internal representation of the word king, and I look at the internal representation of the word man, I find that in this space, right, when I view it as a vector and I think of it as a geometric space, I find that king and man have this kind of geometric orientation to each other. Right? There's this arrow pointing in this direction from king to man. And what's fascinating is that when I look at queen and woman, they have the same geometric relationship. Like the direction in this space, in this internal representation space for the neural network, tells you something about the meaning of words. Like there's lots of other examples on the slide. So when I look at words like slow, slower, and slowest, they have this orientation to each other when you use the network's internal representation. And fast, faster, and fastest have the same orientation. Long, longer, and longest have the same orientation. And you can use these facts in other applications to try to improve other machine learning models. So this is often used in a trick called pre-training. So in pre-training, you give it a whole bunch of text. You give the network a whole bunch of text. You ask it to, you delete a whole bunch of words and you ask, predict the missing words. So now, again, the point is not to solve that particular problem because that problem is useless. But what you find is that the network in solving that problem generates internal representations for every word that is quite meaningful, has a lot of semantic richness to it, and allows other networks, now another network can use that information to solve an actual useful problem like translation or part of speech tagging or parsing or whatever. So this idea of pre-training recently, I would say in the last year or so, has become really popular and really impactful in machine learning. So a lot of the state-of-the-art techniques now are, especially in natural language processing, you give it this enormous corpus of text, you do this pre-training. The pre-training, its only purpose is to try to learn useful representations of words that in some sense encode meaning, and then you use those encodings to solve some actually useful problem. Okay, so here's another example where the problem that you're solving initially seems useless, but it ends up being useful if you look at it the right way. So this is called, the picture, the neural network I'm showing you now is called an autoencoder. So here, the input again is an image, as we've seen many times before. The output is also an image. And the goal, you ask the network, learn weights for this network so that output matches the input. We call this architecture and this problem an autoencoder. So now what's the point, right? Like, why would you ever want a network to simply predict its input? You already know the input. What is this accomplishing? The point is that if you set up the architecture in this way as kind of a bottleneck, then the middle layers, which are much lower dimensional than the original image, they represent kind of this condensed, succinct description of the essence of the image. Okay, so if I give it, like, let's say the input is handwritten digits, and of course there's many possible handwritten digits, but you know, there's only 10 that you can handwrite. So really, I should be able to kind of boil down any image. Like, let's take all the 2s in the world that anyone can ever write, right? Like, even though this is technically a very high dimensional space, like I probably need like maybe 1,000 pixels to represent a 2. It's not a 1,000 dimensional object, the handwritten digit 2. It's not a very complicated object. You can probably represent like essentially what a 2 is using just a few numbers, using just a few dimensions. And that's what the internal layers of these autoencoders essentially learn. They learn in the most succinct representation of notionally high dimensional images, and that representation turns out to be useful when we want to generate new images. So now this is the second half of this autoencoder. So here the input is just, so let me just go back. So like previously the input was the input image, the output is like also an image, and I'm just asking the network to reconstruct its input. Here, the input, this is now just the second half. I'm asking the network just like some input in this latent space, in this like very condensed space that just represents the essential properties of the image. And I'm asking, generate an image from that part of the latent space. So I say, okay, give me a number, give me a handwritten digit 1, and it'll just generate a realistic looking random number 1. And if you run it again, it'll give you a slightly different one. And again and again and again, you can get as many realistic looking handwritten digit 1s as you like, just by picking the right part of that low dimensional latent space. So this is used in generative modeling. So here on this slide, I have a bunch of images of like living room, bedroom scenes. But if you look carefully, you'll see that these are not real images. These are fake images, and they were generated using a generative model. Not exactly like the one I described in the previous slide. It's more complicated, but it's the same basic idea. So it said, okay, you train it on a whole bunch of, a whole bunch of images, and it learns like, okay, basically what a living room looks like, basically what a kitchen looks like, and so forth. And then you say, okay, give me a random kitchen, give me a random living room, et cetera, et cetera. If you guys, probably most of you have heard of deep fakes, right? These deep fakes are models that are used to generate realistic images and realistic videos. Deepfakes are produced using generative models that are trained the way I just described. And these images, if you look at them, they're not even that good. So these images are from the original paper that really kind of came up with the state-of-the-art way of generating fake images, realistic images. But nowadays, I mean, maybe all of you have seen them. Like nowadays, the deepfakes are quite good and almost indistinguishable from real images. Here's a bunch of pictures of realistic looking dogs, although none of them are that realistic. Although one of them actually is written there. Okay. Okay, so that was a tour of all the different models. There's more, but I think those are the kind of the big ones. Now let's talk a little bit about how you train these models. So remember, in all cases, I said, you wire up the neurons in a certain way, then you just ask some algorithm to find the best set of weights. The best set of weights is the set of weights that prediction error. And then we talked about, okay, what are some emergent properties of the network? Like, what do those weights tend to represent? How does the network actually try to solve the problem? But what we didn't talk about is how does the algorithm actually find the best set of weights, right? Like, how do you do it? In a shallow model for recognizing handwritten digits, if there's only a few hundred, you could imagine possibly just like enumerating all possible sets of weights and just finding the one that gives you the best possible prediction error. For much larger models, which have millions of weights, sometimes billions of weights, of course, that's not feasible. So what do you do? How do these learning algorithms actually learn? And let me stress that again. A learning algorithm more than an algorithm for finding the best set of weights in some model to minimize some notion of error. That's all a learning algorithm is. So how do you do it? Well, so again, I'll just restate the problem. So the best model weights are the ones that minimize the error on some error landscape. If you try to visualize the error, right, you can think of it as like a physical landscape. It's this, this is a three-dimensional landscape. If your model has 1 million weights, it's a 1 million dimensional landscape, which of course applies. But basically, you can think of it as like a physical landscape that you're walking around. Different points in weight space are giving you different errors, and you're just trying to find the minimum of the landscape. So what's the problem? Like, why can't we just jump straight to the minimum? The problem is that we can't, as I say, we can't see it, right? Like, it's not, if it were just a three-dimensional object, we could see it. We could just plot it like I did on the previous slide. We could just jump straight to the minimum. But if it's a 1 million dimensional object, we have no idea where it is. But what we can do in almost any case, no matter how many weights are in the model, is that we can see kind of like the local neighborhood of any particular set of weights. So here on the left, I've plotted the error landscape for one dimension. This is a one-dimensional problem. And no matter how many dimensions the problem has, I can always, for any set of weights, I can use calculus basically to figure out what does the error landscape look like in the neighborhood where I am right now. Okay, so I have a set of weights, I use it to make predictions, I compute the error, and then I can use calculus to figure out what would the error be if I change these weights just a little bit in any direction. Why is that a useful thing? Because now what I can do is I can try to get to the bottom of the error landscape by iterating the following process. I pick some set of weights just randomly. I use calculus and on the data what the error would look like if I were to take these weights and just change them just a little bit in any given direction. And then I actually do change the weights in the direction that reduces the error as much as possible. Then I just process. And if I were to make an analogy with a more physical analogy, I would say, imagine you're on some undulating landscape, like I showed you a couple of slides ago. I'm trying to walk to the bottom. I can't see anything. I'm blindfolded. But what I can do is I can take little steps in any direction, and I can feel which direction is downhill. And so I just take one step downhill, and then I feel around again. I take another step downhill, and I keep walking in that way. And if I keep walking in that way, then I'm going to end up at the bottom of the error landscape. So this procedure is called gradient descent. And if you learn nothing else from this talk, you should learn that gradient descent is the basis for essentially all modern machine learning algorithms. That's all there is to it. So when someone says I have a learning algorithm, what they're telling you is that they have an algorithm for performing gradient descent in some error landscape. So there's lots of challenges to gradient descent. It's not quite as simple as I just made it out to be. One problem is I have to choose what's called the step size correctly. So again, going back to the analogy, I'm walking on a landscape, I'm blindfolded, I can't see where I'm going, but I can take. Oh, is there a question?
Yeah. Can you hear me?
I can hear you.
I posted the question to the chat box. Are you going to email us these slides at the end of the presentation?
That's a good question. I think I'm not. I think I may not be allowed to. I think I have to ask my company whether I can do that, and I sense that they're going to say no. But I do think that the video is being recorded. So if you want to watch the recording later, you can do that.
Oh, we can't. So how will we be able to do that?
It's on the ICNYU page, Facebook page.
On the Facebook page?
On ICNYU, Islamic Center at NYU.
And it'll be there, the link?
Yes, we're live streaming through that too.
Okay, so you're live streaming through Facebook, so you're saying we can go to your Facebook page after this and find the link?
Yes.
Okay, thank you.
You're welcome.
Okay. Right. Okay. So you're walking down a landscape, you're blindfolded, you can't see where you're going, but you can take little steps in any direction and you can feel which direction is downhill. And so you take a little step in that direction and you keep going and hopefully you get to the bottom of the hill. What are some problems that can arise in that procedure? One problem is that the steps you take are just too small, and so it just takes like too long for you to get to the bottom of the hill, and so your training algorithm, your learning algorithm is going to take forever to find the bottom of that error landscape. Another problem that you might have is that the steps you take are too large, right? Like rather than taking a little step, you take big leaps, and so you kind of like bounce around the middle of you bounce around the landscape and you never reach the bottom. Another problem you can have is that maybe your landscape is steep in one direction but shallow in another, and that can cause you to bounce around in a slightly different way. So all of these problems have solutions. And so basically, but they're all basically more sophisticated, fancier versions of gradient descent. Another problem you might have is that this landscape, right? It may not be just a simple bowl-shaped thing. It may be maybe this undulating landscape. And you can get, even though you walk to the bottom, you're not really at the bottom because you get stuck in what's called a local minimum, which I've depicted here. And so you can try to solve this in different ways too. Like you can just try to like randomly move around the landscape so that you jump out of the local minimum. You can try one perhaps surprising way of solving the problem is just not to worry about it. You just deal with the fact that you're not at the very bottom and just go on with your life. That kind of works pretty well too. There's how many slides do I left? Yeah. Okay. So there's also the problem of overfitting. So I give you loads and loads of data, right? And you try to find the set of weights that has the lowest possible error on this data, but you don't really care about the data that I've given you. You care about the data that you're going to see down the road in the future. And a risk of trying to find the lowest possible error on the training data is that you're going to overfit it. You're going to learn just coincidental regularities that appear in the data that you're learning on that don't appear in data that you're going to see later on in the real world when you're actually deploying this model. And so there's various techniques to try to address that as well. You can try to rather than making the model perform really, really well on the training data, you can try to handicap the model a little bit so it doesn't perform that well on the data you give it, in the hopes that it'll generalize better to unseen data. Okay, and so I think I should wrap up as soon as possible. So a question you might ask yourself is, why did it take so long for deep learning, for deep models to become popular? I mean, the idea of taking neurons and hooking them up to each other is pretty clearly motivated by the architecture of the brain. And it's so clear that people have been thinking about it since the 1950s. A lot of the models that I talked to you about today were conceived, at least, back in the 80s and 90s. But why did it take until like the 2010s for this stuff to really take off? And I think there's a couple of reasons. One is when people were trying to train these models back in the 50s, 60s, up to the 80s or 90s, they just didn't have enough data and they didn't have enough compute to train them. Because these deep models, they have a lot of parameters and you use a lot of data and a lot of compute to train them well. And it took a lot of time for just, the horsepower that we have available to us now to catch up with the size of the models that we were trying to train. And I think and this is sort of just my opinion, my editorial opinion, is because these models were so hard to train, people just didn't try to train them. And so a lot of people just just didn't even give it a go. And it took some researchers who had some guts and some appetite for risk, and they said, let's try to train these models on some really big problems and see what they can do. And I think it was a surprise to everyone when they found out that they worked as well as they did. But it took some courage to try to train a very complicated model when you're the first person to ever try to do it. Maybe I'll skip over this and just skip to the end so there's at least a little time in case there are questions.